Afternoon, everyone, and uh, thanks the organizer for kindly inviting me. And I would like to actually apologize in the beginning, right? Because I'm on a very tight schedule, so my talk will be a little shorter, and I will be taking two questions. And I have notoriety because I may not go actually deeper for some of the folks here. And please, my email will be here, and please get in touch, and then we can converse later also. Um, so to move forward, essentially, over the last 5 years, we have tried to actually explore something and to bring a design change in the way that we know the ICs today, and that's actually what you are seeing here is sort of this is basically an op-amp. It's on actually it's bonded on this PCB. And now it's been completely have been transformed into a compliant architecture. You can ignore the butterfly. It's just for the fancy. It can be any shape. But what's really happening is that essentially the core of the silicon, which has been flexed, and all the fan out and all those have been taken care of, and the packaging has been changed with 3D printed, and it becomes completely compliant. And my talk today will be centered around this. Um, going forward, let's first the typical what, why, and how. Some of the examples from our own work. So the smart living constitutes the quality food. You can see some of these compliant sensors which have been widely deployed in agricultural farm using the drones, which essentially gets the microclimate monitoring as well as the condition of the plant itself. This is for purified water, which is essentially the microbial fuel cell, which takes the the you can say the filthy water and can purify it while generating electricity, which is the only known the viable technology which can do the both the water purification but without consuming any power. This is an example of the clean energy, the transformation of the windows. So this specific window, this could generate the nearly from 100 square feet window with a 20 degrees Celsius temperature difference, like 300 watts of power. This is a clean environment to understand the some of these what's really happening in the the aquaculture. So essentially the blue crab of our the Neva Red Sea, we're wearing the compliant sensor, which is a 6.4 gram compared to the kilogram level of bulky elements, which can actually do the environmental monitoring. This is essentially the safety and security, which means is if someone's data has been stolen through the hard drive or the cell phone, so you can remotely the in a sense destroy it, the silicon chip with the memory blocks. This is the convenience in life, which is 360 imaging, which can simultaneously take image from all different sides. These are all the silicon based photo detectors. They're connected via spirals, so they can actually elongate. At the same time, these are 3D printed, so each of them behind them, so they can actually come out and dynamically focus for each of these pixels. The next one is sort of that how this is where I will actually have some emphasize later in my talk, how to use sustainable materials, which are essentially you can find off the shelf, and how you can use them to build electronics, not the logic computers or the memory devices, but rationally the sensors, that kind of the technologies. And finally, one of the examples from affordable quality healthcare. This is a version of the the precision thermotherapy using flexible and stretchable format of micro heaters, which are connected via this spiral design. So they're so thin that they're compliant, as well as they can be stretched out. So for a small area you can wear it, at the same time for large area you can also stretch out and wear it. And they have the electronics associated with them, the compliant one, which can actually be used for the essentially for pain management. So now, if that's a broad spectrum of smart living, which is essentially telling us one thing, and that is the excessive proliferation of electronics technology in our daily life. and why this can actually be inspiring. So this example is kind of very interesting because it says that to print a book which is containing whatever the information here, that will require this much of gallons of water, compared to if you just have an e-version of that book, it's gonna actually take you only 2 glasses of water. So it's smart living is the essence of also the sustainable future. So that's essentially the the possibility, the opportunity, and the possibilities. If you look at, then by 2030, the expectation is there will be trillions of sensors. And if that's the case, then the deployment of the sensors to make sure that they're of low cost, they're accessible, they can actually that they can be integrated with also the natural species, as well as the maintaining seamless communication in a secured manner, and to analyze the data and to make sense of the data, and then to use the data to make decision and to let the electronics, which will also be integrated with actuators, to really complement some of our work and to help us out. So there is this both the opportunity and the possibilities, they exist, they coexist. Now, how? I think that I have always been motivated in my adult life by two questions: is why and why not. Just to give an example, and one example is we always hear about smart cities. Why don't we hear about frequently on a smart village? I think there is a little bit of the affordability issue. We don't consider that the people who are not living in the urbanized location, that they can have also this kind of electronics. Just take an example of the smartphones. And another example would be that, as I said, this is from Ali Javi's work, and also IMEC has shown something like this. This is from Professor John Rogers' work. Also, I personally have some reservation about this specific, the outlook or architecture of the ICs, and that's why we have actually tried to make them why not so boring, why not they're poetic. So just to make something like this, so it gives them an identity, it becomes compliant without compromising any of the performance, integration, density, reliability, and energy consumption. Having said that, so now there are some the interesting challenge, because the status quo for this, which I will show you in a moment. But let's see, for a simple sensing system, we do need power supply, power management, driving circuitry, sensors, readout circuitry, microprocessor, and transceiver. So this is for data management. This is for data communication. Now, if you look at the spectrum of the electronics that exist today, the logic, memory, power, sensors, actuators, RF, analog, energy, medical, and automobile, and if you take what's really happening, so essentially, we cannot consider a logic device which will not have performance, means the data processing speed very small, so that we can actually integrate them a lot, as well as they have to be energy efficient. The same is true in a sense for memory devices. Now, if you look at the current status quo for flexible and stretchable electronics, is to use one-dimensional carbon nanotube or other kind of nanowires, organic molecules, or two-dimensional materials like graphene or dichalcogenide materials, which are naturally flexible and stretchable, and to use them. On the other hand, there is the materials which exist, which we use all the time, like silicon, gallium nitride, silicon germanium, or T5, they're inorganic. Now, if you look at from the perspective of performance, the integration, the density, and from energy efficiency, definitely the inorganic are much more reliable and they stand out. And yet they have to make a lot of progress to actually to reach there and to beat them, right? So the challenge with inorganic is they are not flexible. Mostly they are rigid and bulky, and they're not stretchable either. So in my consideration, we actually have an opportunity in context of heterogeneous integration to actually use the inorganic material where they must have to be used, and to use and to fuse these kind of new emerging materials as they are applicable and suitable in context of their suitability for these different electronic applications. So having said that, then the big question is that why cannot we use the small ICs that we hear that, okay, the ICs are very small. So this is actually, if you start looking into the broad spectrum of what we are hearing on the healthcare technology, the amount of data that's going to come out, or they're expected, like, so they require larger ICs. You just go and do a Wikipedia search in Intel microprocessor, you can see that the years after years, while their performance and functionalities are increasing, their chip size is also increasing, while the transistor size is shrinking. We do also hear that RFID and NFC, but they have limited memory and used for data exchange only. And if you think about, like, that they don't do the data processing, which is also very important, even if you think that all the sensors are going to be connected to, like, in a nodal way of distributed computing. Also, like, if you take, like, the simple system like Raspberry Pi Zero or something like that, that's actually, pretty large compared to, like, the way that we think about this. This is not something someone will be very happy to put in the intracranial space to do brain-machine interfacing. There is also issues. Let's assume that even if we actually take the silicon ICs, bare die, we pin them down and put them on the flexible PCBs. If they're, like, the strong adhesive is there, then they are going to actually break with even a bending radius of 5 centimeters, which is essentially nothing. And if they're poor adhesive, then they're going to pop out. There's also the heat management issue, that localized heat, hot pocket formation, which is actually restricting us to use the ICs. And at the end of the day, from just a curiosity purpose, that why they have to be looking like the way that they look like. So the question is that what's the way that we can actually flex the inorganic materials which are rigid and bulky? The very simple example, if you take a dictionary, there's thousands of pages, so they're sturdy, strong, hard, but if you take out only one page, you can crumple it. So essentially, if you can make things thinner, then their flexural rigidity goes down and they become flexible. And based on that, from the long time back, it has been done. I think the year I was even born, so that was with the 3.5. But Professor Max Lagali of Wisconsin-Madison, he started using buffered oxide, the SOI, and then it was popularized initially by John Rogers, and then he moved to use some other, the substrates on the silicon. But let me show you what's happening. So basically, when we are building devices, we also need to have isolation in between them. Assuming that if we are making like a FinFETs, like something like this, okay, so because this is buried oxide layer, so we can actually etch off and they are isolated. Or we can use a very thick SOI with, we can introduce shallow trench isolation. By the way, this is extremely expensive. Or we can do the dinosaur age, the mesh isolation, which actually causes the bird's beak, right? So why the SOI is kind of interesting, because if you remove the box, then you can have all these SOI level, which is essentially now flexible. But this is what's happening. So these all are discrete devices, they're floating away. And this one is extremely expensive, and this one will have so much board that it is actually non-usable. Okay, so people can argue that why don't we actually unpack the ICs and then do the back grinding. Hynix does it all the time, but that also, because of its abrasive nature, you can do it up to a certain extent, which will not give you the flexibility that you are looking for. You can buy from Virgin Semiconductor, the ultra thin or extremely thin silicon, which according to their own admission in their website, it has extreme defects. At the same time, after one or two of the thermal budget processes, you will see that they are actually bored so much that you cannot, the next, the equipments, they are not going to even accept them for further processing. Okay. First by UT Austin and then by IBM, they have been trying, they're using metal stressor, but to spall, to do intentional cracking. But what happens is, for every material change, for every geometric layout change, you have to figure out or reinvent that what is going to be your material system. And definitely, if there are hanging devices, the MEMS devices in the back end of line modules, then you don't expect that they're going to survive when this one has been removed. So having said that, that actually shows that why in the silicon we are not using the other orientation of the silicon. Now this one is the one which actually is used to make 90% of the electronics today. This is the one which Professor John Rogers has popularized. But if you look at, the defect density is so high that except for BiCMOS, it's not used in any kind of the logic computation or the memory device purpose. So that actually shows clearly that there is opportunity window for manufacturability. Having said that, so we started with all the time we start with some questions that 90% of the electronics, they use bulk silicon 100. The question is, can we flex such electronics? Can we maintain the performance? Can we retain the integration density? Can we do it using CMOS technology? Can we keep the cost low? Can we reuse the substrate? Can we use it for other materials, expendable or not? And can we make flexible 3D ICs? So we have developed on the various of techniques, all are CMOS based to actually to relieve or release the flexible portion of the silicon with all the electronics already prefabricated. And I'm going to actually run this video. Hopefully it actually shows that the student is taking off, which is a 4-inch silicon wafer with all the electronics, and they are now coated with a hard mask. And when it's being done, you can see at some point that it will be completely relieved, and that when we remove all the the hard mask, then you can see that all the electronics are there. Now, during all these processes, now over the years we have come up with the variety of processes based on the applications, based on thermal budget, the presence of the materials. These are all complex issues which are so it's been released, and you can see that at some point he's going to actually show that it's they're fairly flexible. So we have demonstrated back in 2014 in Advanced Materials as a cover article, the sub 20 nanometer FinFET circuitry on 0.5 millimeter bending radius of the silicon substrate. So now one of the interesting points is, just take an example of the brain machine interfacing. So the brain allows only 64 centimeter square area for sensing. Now if you have sensors, then you also need the transistors to actually understand what the sensors are sensing. So if you put them in a monolithic manner using in-plane integration, then you're going to have the sensors and the transistors sitting side by side. So it means that I'm giving away my precious area for sensing for transistors, right? So if that's the case, so if there is a way that like a coin, if the other one side is sensors and the other side are the transistors, and the in-between medium, which is actually it can be pretty soft, and we can have through those soft material via, then we can save the sensors and we can take the transistors away, which also dissipate heat. So this is one of the examples that the sensors are touching a silicon substrate. On the other hand, the transistors on the other side. This is the various kinds of polymer, and also because the way that we fabricate them, there is translucency is there also. So having said that, if you look today that what's being done in Intel, I came from industry, I worked there for 5 years. So this is exactly where on 12-inch wafers you make all your devices. Then you use the dicing machine to have your bare die, you package them, and then they go on a PCB so that you have a system, right? So what we have done is come up with okay, so we build the devices exactly the way that those are being done. So we don't compromise the performance, integration density, or anything like that. And then we flex them using various techniques that we have developed. And then we use laser dicing to make the small pieces, because these are thin, they're fragile, but they're flexible. And then we come up with we developed an equipment which actually with a vacuum suction, pick them up and then place them where they have to be. Now the big question is that this was actually it could have been an IC. We don't want that. So rather we went to the silicon and then having all the fan outs. So the reason that they are actually moving away, because if you would like to do it in a very small area on the soft substrate with a fragile the silicon piece this bonding, it's nearly impossible. But if you have a little bit of separation from the origin, then you draw it on the farther, then there are much more separation area than you can do it using the sputtering and clipping and many other different techniques. Just to give an example, so what we did on any of the ICs on the silicon plane, on the one side has the electronics, but the other side is plain and flat, right? So we started giving them some of the texture, the triangle, whatever the shape you can think of, the different depth or height, as well as different sizes. And then we had soft substrates where we actually formed the groups accordingly. So let's assume that IC 555 that has a triangle or a heart shape, and that has only one group where it will fit. Then we draw the lines using inkjet printing, and and then we float them. So now let's see if this actually works out fine. So this actually, you will see that these are like, this Lego shape. So the machine is actually like, the scanning, and then it will pick it up and will place it on a soft substrate where, because of their placement, it makes the connection and the LEDs is on, right? So this is how, like, you can simplify the way that this kind of electronics can be made. And this exactly like, that our objective is keep the active as they are, or to make it better. And then let's look at the passives, if somehow we can actually go and start replacing them so that we can make them compliant and we can make them more pervasive. Okay, so the question is that why we are getting this democratized. So at some point, like, that we wanted to actually see that if there are, like, the commonly used materials which can be used without any kind of functionalization for, like, these purposes. And we needed actually an engineering motivation. Like, the skin is something which is very interesting because it has multisensory functionalities. At the same time, like, that there are thousands of people, they need skin treatment, like road accident, burn victims, acid victims, battle wounds. One of the interesting things in skin, there's like, that where let's assume that if I have an ice cube and I'm placing it here, I'm not going to only feel the cold. When I press it, I will also feel that air pressure. So in a same single spot, at the same time, we can sense multi-sensing, right? So the skin itself is very interesting because it has placed these sensors in a three-dimensional out-of-plane architecture. So in one spot, when we do the sensing, it actually, the others also sense exactly the same way. So this is when we started, we did it on the breadboard. It looks like that. This is from Professor Taco Somea. This is from Zinan Bao. This is from Ali Javi. They have done pressure sensor, like on the, as well as the tactile sensors and temperature sensors. But we wanted to take it further. So what we did, we looked into that if we can use the resistive and capacitive sensing where you don't need any kind of semiconductor. You go to your kitchen, you can get sponge, you can get like, sandwich wrap, which are insulator, you can get aluminum foil, copper foil, which are like, the electrically conductive. And if we start like, the cutting them into different sizes and shapes, then you can most probably have resistive and capacitive elements. And based on that, we started actually looking into, can we use recyclable material? Yes, they are. Can they be used as they are? Yes. Can we tune the functionalities? Yes. So some of these, as an example, like, that the proximity sensing, so where your iPhone doesn't necessarily need to be touched, so from 1 centimeter or 1 inch, you can do one functionality, from another distance, you can do another different functionalities. Obviously, there are more optimization can be done, but the concept exists. And they be robust, like, there are civilizations where thousands of years, like, that their knowledge have been stored in the paper. Can they be reliable? Up to some extent, yes, but mostly disposable. Can it be multifunctional? And anyone can make them. So we started actually making them, yes, like, anyone really literally can make them. These are, some of them are made with, like, the county schools grade 2 and 3 students. And when you start placing them on top of each other in an out of plane, then you can make environmental monitor where we are showing, like, the simultaneous sensing from the same spot. If you would like to do body vital monitoring like heart rate, temperature, skin hydration, you have to do it in in-plane integration. Some of these examples are here, like in the millennials, they like, the band. So we have worked on this. And this is actually an extremely low-cost version of, like, the paper watch. We have an yearly event of pilgrims where 3 million people show up, and most of them, they're Egypt. They don't know a communicable language in a sense. So we just actually started making it for them so they can do, like, the temperature and heart rate sensing. So if someone is 10 hours immobile, then it will send a note so someone can go and interfere what's really happening. So essentially, to summarize in a sense, I do believe that going forward, sensor and actuator integration is critical because that will help us to make in a miniaturized version, like on the smart or interactive electronics. I do also believe that the freeform electronics will give us the the freedom to deploy it where we want, especially integration with nature or biointegration. And finally, democratized electronics, affordable to anyone and accessible to all, means that easy to learn, simple to implement and use. And that will actually usher into innovation because a problem in a village in Tanzania should not necessarily be always solved by Apple. It can, if there are open source, if there are materials are available, they should be able to take care of them at least in a rudimentary fashion. That's how we see. And finally, obviously, I do see that there is an expansion of CMOS technology is possible with the up and coming 3D integration, fusing with new suitable materials and processes like 3D printing, electrochemical deposition, imprint lithography, self-assembly will make it happen. So this is where I will rest, and we'll be happy to take 2 questions. Thank you so much.